Hello, everyone. Welcome to another ZX seminar. Today we have Yehua Liu, who will be talking about fault-tolerant complexes. Yeah, take it away.
Yeah, hi, everyone. I'm Yehua Liu from PsiQuantum. And today I would like to share with you our recent work on fault-tolerant, sorry, let me get this. Yeah, on fault-tolerant complexes. So this work is a result from our continuous effort in designing fault-tolerant protocols for fusion-based quantum computing. And we believe it has a wider range of application thanks to a synergy with the ZX calculus. So this is actually my first time talking about this work outside of the company. So please feel free to ask questions during the talk if anything is unclear or confusing. So here are the main results. So in this work, we propose a unifying framework for describing fault-tolerant protocols based on 3D cell complexes, which we call fault-tolerant complexes. And this framework reviews the parity check structure for fault tolerance in the protocol, which is missing on the ZX diagram representation for the same protocol. And roughly speaking, this is because a 3D cell complex contains more information than its one skeleton, which is a graph. And next, so this framework enables extensive computer search for candidate protocols, thanks to the computational tiling theory. And last, this work is applicable to different flavors for quantum computing via ZX calculus. Here, different flavors, we mean circuit-based quantum computing, measurement-based quantum computing, or fusion-based quantum computing. So as I mentioned before, this work originated from our study on fusion-based quantum computing, which is the main focus at PsiQuantum. So I will first give a brief introduction on fusion-based quantum computing. And then we will move on to fusion complexes, which is the main body of this work. Specifically, we will talk about the geometric structure of fusion complexes, its ZX calculus picture, and how we perform computer search for candidate protocols, and finally, the homological perspective of the construction. And next, we will show that the results from fusion complexes can be applied to other flavors for fault tolerance thanks to ZX calculus. And the last are some further generalizations of the framework. So in fusion-based quantum computing, or FBQC, the quantum computation is realized by first preparing resource states and then perform fusion measurements on the resource states. So here, the resource states are small entangled states on a few qubits, and the fusions are field body measurements among the resource states. And in this talk, we will focus on the simplest two-body, two-qubit measurement in the XXZZ basis, which we call a type 2 fusion. So at PsiQuantum, these two primitives, the resource state generation and the fusion measurements, are realized in hardware using linear optics. And on the right is the schematics of the protocol. So here we have an array of resource state generators, and they generate resource states at constant rate in time. So these resource states are represented by these red 6-qubit rings. So we have 6-qubit resource states. And after the resource state generation, the states are consumed by the fusion measurements. So here there are type 2 fusions, which are highlighted by these yellow thick lines. And then after the measurements, we get a lot of classical outcome. So they are binary, and they are represented by these 0 and 1s. So we know that large-scale quantum computation will require fault tolerance. And in fusion-based quantum computing, the fault tolerance is achieved by the existence of parity checks on the fusion outcomes. Here, a parity check means the sum of certain binary fusion outcomes must have a fixed parity. And parity checks allows for decoding of errors. During this whole process of resource state generation and fusion measurement, the logical qubits for the quantum computation are encoded and transformed in space-time. For example, the focus of the fusion complexes will be the logical qubits are encoded in their surface code. Here is an animation of the process with the resource state generation in time, fusion measurements, and the gathering of classical data. So theoretically, at PsiQuantum, we represent a fusion-based quantum computing protocol on a 3D lattice. So on the 3D lattice, we have vertices and edges. And here, each vertex represents a resource state, which is described by a certain stabilizer group. And every edge in the lattice represents a type 2 fusion, which is, as we mentioned, is a two-body measurement in the XXZZ basis. And parity checks on the fusion outcomes are represented by webs of edges in the lattice, something like this. And it turns out that in FBQC protocol, in this protocol, every fusion outcome participates in 2 parity checks. And this allows for graph-based decoding. For example, we can use the union find decoder or the perfect matching decoder for the decoding. And prior to this work I'm talking about, FBQC protocols were constructed manually in the following way. First, we have the resource state group R, which is the tensor product of all the stabilizer group from all the resource states in the lattice. So it's a big group. Every element in this group have fixed sign because we have control over the resource state generation. We also have the measurement group or the fusion group M, which is the tensor product of all the type 2 fusions from all the edges in the lattice. It's also a big group. So individual measurements in this group, if we perform the measurement on the resource state group, might have a random binary outcome. So individual ones might have random outcome. But if a certain product of the measurements in this group is also belong to the state group R, then we know the corresponding binary outcomes must have a sum that has a fixed parity. And that is exactly a parity check. So don't worry if it is not, this is not super clear yet, because later the fusion complex picture will make all of this much easier to understand. So when we design fault-tolerant FBQC protocols, we look for favorable properties. So first, we want the resource states to be small because small states are easier to prepare in hardware. And more importantly, we want high threshold for error correction such that we can tolerate more noise in the hardware. And for this purpose, we can look for low degree checks. So here, a check degree simply means the number of outcomes participating in the check. For example, here we have a check with degree 12. So lower check degrees are better, because they are more informative for decoding. So these are the 2 favorable properties, but in general, for each individual protocol, we cannot achieve both at the same time. So we will need to make trade-offs. One way of doing this trade-off is by first proposing a lot of different FBQC protocols, and then we perform down selection. And for this purpose, a manual design is not ideal. So this situation actually motivated us to study the general structure of FBQC protocols, and specifically what kind of geometry allows for an FBQC interpretation. And here are some important questions to be answered. The first one is, where does the 3D lattice come from? And then, what is the resource state stabilizer group for each resource state, which are vertices in the 3D lattice. And then where do we look for parity checks? And finally, most importantly, is there a simple criterion on the underlying construction? In the fault-tolerant complexes paper, we answer these questions in the following way. So the 3D lattice is actually a one skeleton of a 3D cell complex. So here by 3D cell complex, we mean a tiling of 3 dimensions in terms of vertices, edges, faces, and cells. And the one skeleton is the graph made from the vertices and the edges of the 3D cell complex. So on the right is an example of the cubic complex, the cubic cell complex, and its one skeleton, which is the cubic lattice. So on the cubic cell complex, the cells are the cubes and the faces are the squares. But on the one skeleton, which is the cubic lattice, we only keep the edges and the vertices. And next question, what is the resource state stabilizer group? Remember, on the 3D lattice, every vertex represents a resource state. So it turns out the stabilizer group of the vertex is determined by the incident edges and incident cells of the vertex. And next, where do we look for parity checks? And it turns out the parity checks are actually cells of the cell complex, and each cell is a parity check on the fusion outcomes from the incident edges. So remember, edges in the lattice represent fusions, right? And finally, there is a simple criterion for the underlying construction, which is the 3D cell complex. And the criterion is very simple. We only require that all edges in the cell complex have 4 incident cells. So let's see how this works out in an example. So here we use the simplest possible example, which is the cubic complex. So this example will be specific, but our arguments for the consistency requirements will be in general. So there are 2 main consistency requirements. The first one is the prescribed resource state stabilizers do commute with each other. And the second one is that the prescribed parity checks do have fixed sign. So let's look at the cubic complex as the 3D cell complex. First, it is easy to check. It is indeed the case that every edge in the cubic complex has 4 incident cells. So it indeed satisfies the fusion complex condition. And because of this fact, we can have a bicoloring of the cells in terms of 2 colors. Here we use blue and red, such that every edge is incident on two blue cells and on 2 red cells. For example, the edge here that is perpendicular to the screen is incident on these 2 red cells and on these 2 blue cells. And in this talk, we will assign for the bicoloring, we will assign blue color for the Pauli Z operator and red color for the Pauli X operator. And then let's look at a vertex in the cell complex. So every vertex in the cubic complex has 4 incident edges. And that means all the resource states in the cubic complex are 6 qubit resource states. Also, every edge is incident on 8 cells. And there are 4 blue incident cells for a vertex, corresponding to 4 Z-type stabilizers on the resource state. And there are 4 red incident cells corresponding to 4 X-type stabilizers on the resource state. So a simple counting shows that there are 8 stabilizer generators for a 6 qubit resource state. This is because 2 of them are actually redundant, exactly as on the surface code on closed surfaces. So here is a more detailed look at a vertex in the in the cubic complex. So here we are interested in the center vertex in this figure. and we plot this vertex together with each of its 8 incident cells here. So in the fusion complex construction, resource state stabilizers are determined by the corners of the incident cells of the vertex. A blue corner describes a Z-type stabilizer, and the red corner describes an X-type stabilizer. For example, the vertex here we are interested in has this blue incident cell, and there is a corner here, the blue cell and the vertex shares 3 edges, number 1, number 5, and number 6. Because of this, there is a resource state stabilizer, which is Z1, Z5, Z6. And similarly for the other 7 generators. So here we can already show that the X and Z stabilizers, they do commute with each other. And this is because if 2 incident corners in opposite colors, if they have any overlap, they must overlap on 2 edges. For example, we have this incident corner here in blue color on 2, 4, 6, and we have this red incident corner here in red color, which has edges 5, 4, 6, and these 2 stabilizers, they overlap on 2 qubits, so they do commute. But this is general for any fusion complex as long as it satisfies the fusion complex condition. So this is general. Now let's look inside a resource state. Again, thanks to the fusion complex condition, inside a resource state, every qubit of the resource state participates in 2 X-type stabilizers and 2 Z-type stabilizers. And it turns out that every resource state is a surface code state on a topological sphere centered around the vertex. So this is a full rank state without any logical degrees of freedom, because it is on a topological sphere. Now let's show that in the fusion complex, the cells are indeed parity checks. So there are 2 equivalent viewpoints on all the Pauli operators on the incident edges of a cell. For example, for this blue cell, we first have the vertex viewpoint, where the product of all the Pauli Z operators on the incident edges is decomposed into the product of Z resource state stabilizers from each incident vertex, just like this. This is the first viewpoint, the vertex viewpoint. And we know that this product decomposed in this way must have a fixed sign because it is in the resource state group, the group R I mentioned before. And then we have the edge viewpoint. So the same product of Pauli operators can also be decomposed into this way, which is the product of ZZ fusion outcomes from each incident edge of the cell. So these 2 viewpoints are equivalent. So the second viewpoint also have a fixed sign. And this means a product of fusion outcomes has a fixed sign. And this is exactly a parity check. Again, this is general for any fusion complex. And similarly, we have parity checks on the XX outcomes. The existence of parity checks allows for the decoding of errors. And in this talk, we will focus on the simplest error model, where we assume all the resource states are perfect, but the fusion measurements are noisy. And because of the fusion complex condition, every outcome participates in 2 parity checks. And this means we can formulate the decoding problem on a so-called decoding graph in the following fashion. For example, this is part of the ZZ decoding graph. In the decoding graph, every edge represents a noisy outcome, and every vertex represents a parity check. So the ZZ outcome from this fusion connects 2 parity checks, which are at the centers of the 2 incident Z-type cells. Similarly, there's also a decoding graph for the XX outcomes, and they are disjoint to each other. And in both the ZZ decoding graph and the XX decoding graph, the check degree the number of edges incident on all the vertices in the decoding graph is constant degree 12. So on the right, we show that we have this kind of a structure where an edge in the fusion complex, an edge in the XX decoding graph, and an edge in the ZZ decoding graph intersect each other and form this triple structure. Again, this triple structure is general for any fusion complex. And later we will come back to this when we talk about the triples and the homological perspective. So before we move to the next topic, is there any question for now?
There's a question from Lucy. So maybe Lucy, you should unmute.
Yeah. Okay, thank you. Yeah, it's great. I just I guess I'm missing some background in that. I'm not sure where are the qubits living exactly?
Yeah, so the qubit, so it's like on every edge in the 3D lattice, there is a qubit from this side of the resource state. There's also a qubit from that side of the resource state, because every edge is the 2-qubit measurement. So you can think like every edge has 2 qubits on it from the 2 sides.
Like near the 2 sides, like there are 2 qubits. So it's like, so for the vertex operator, you are talking about acting on the qubit that's near that site.
Exactly, yes.
And then when you do the XXZZ type, you kind of connect it.
Yes,
okay, that makes sense. Yeah.
Thanks for the question. Really clears up. It's like this, right? When we in this picture we talk about the qubit near the vertex, that qubit near the vertex. We are in this picture, we are connecting them by a measurement.
Thank you.
Thanks. Yeah, so next we talk about the connections of the fusion complex construction to ZX calculus. In particular, we will show that for every fusion complex, there is an underlying ZX diagram, and the parity checks on the fusion complex becomes the so-called Pauli webs on the ZX diagram. So Sarah has kindly reminded me that people at PsiQuantum might be using non-standard conventions and notations. So please first allow me to introduce our conventions for this talk. So for the purpose of this talk, ZX diagram is simply a network of spiders. And we have 2 kinds of spiders. We have the green spider, which represent n-qubit GHZ state. And we also have the red spider, which represent what we call a GHX state, or a Hadamarded GHZ state. And in our work, we extensively use a graphical representation of the spider stabilizers. And here is an example. For a green spider or a GHZ spider, there is the all-qubit X stabilizer, which is represented by highlighting all the edges in a color assigned to X. And we also have pairwise Z stabilizers for the green spider, which is represented by highlighting pairs of edges in a color assigned to Z. Similarly, for the red spiders or X spiders, there is also a graphical highlighting, but in the opposite colors. And the graphical highlighting in each individual spiders will connect into webs in a ZX diagram. And we call these webs Pauli webs. So here is an example of the Pauli webs of the C0 gate. So here is a Pauli web. The X stabilizer of the Z stabilizer of the bottom red spider is connected to the Z stabilizer, pairwise Z stabilizer of the top green spider. So this is a Pauli web. And similarly, we have other 3 Pauli webs, which are all connections of individual graphical hightings from individual spiders. And with this introduction, let's look again at a vertex in the fusion complex. As we mentioned, each vertex in the fusion complex represents a stabilizer group. And we can expand this vertex into a ZX diagram with a qubit outputs. Such an expansion is always possible because we have this kind of CSS state, which can always be made from doing X stabilizer measurements on the all zero state. And there will be a ZX diagram corresponding to this process. And further, we can apply simplification rules on the ZX diagram. The result of the expansion for the 6-qubit resource state in the qubit complex is this 6-ring ZX diagram. And after this expansion, resource state stabilizers becomes Pauli webs on the ZX diagram. For example, we have shown that this resource state has a particular stabilizer, which is the Z1, Z5, Z6. And after the ZX diagram expansion, the same stabilizer becomes this Pauli web. So externally, 1, 5, 6 are highlighted, and internally there are also 2 other edges highlighted. So this Pauli web is made from 3 individual spider stabilizers. So that is the connection to ZX calculus from a vertex of in the fusion complex. And now let's look again at the cells of the fusion complex. So previously we have this structure to show that there is indeed a parity check for each cell. And then we perform the vertex expansion around every vertex, incident vertex. And then the individual Pauli webs on the individual vertex expansions will connect to each other and to form a closure. So everything connects to each other and they close around this cell. So it turns out a closure of Pauli webs or closed Pauli webs represent a parity check on the underlying ZX diagram. So here we want to emphasize that the existence of the cells is the additional information provided by the fusion complex condition, which is not apparently present in the ZX diagram formulation. So that is how the fusion complex framework helps us to understand the underlying ZX diagrams for the same protocol. So this framework of the fusion complex allows for extensive computer search for candidate protocols. And previously, this was done for the computer generation of fault-tolerant cluster states for measurement-based quantum computing. And in this case, this is achieved by enumerating 3D cell complexes using computational tiling theory. And in this enumeration, every 3D cell complex is represented by this kind of a mathematical symbol called the Delaney symbol, the D symbol. So our computer generation is inspired by this work. We also start from generating 3D cell complexes, and we use an open source software called Gavrog. And in addition, in our case, we need to filter the results by the fusion complex condition. And the result of this search is a list of D symbols, and each D symbol represents a fusion complex. On the right, we also record the distribution of parity check degrees and the resource state sizes within a unit cell. And here are some examples of the computer search. On the left are the unit cells for the fusion complexes. And on the right are the ZX diagram expansions of the resource states. And previously, we have talked about the qubit complex, which has this unit cell and has this ZX diagram expansion for the resource state. And for every of the unit cells on the left, we can repeat the unit cell in 3 dimensions periodically. And the result 3D cell complex would allow for bicoloring, allow for interpretation of vertices as resource states and cells as parity checks, exactly like the qubit complex example. And here are some examples of the computer simulation of fault tolerance. So here we are using the previously mentioned error model where all the resource states are perfect and the fusions are noisy. So we study the threshold on the fusion errors for both erasure error and Pauli error. And here we can already show some trade-off, like we talked before. So comparing the qubit complex and the so-called 4-star complex, the qubit complex has a larger resource state, 6 comparing with 4. And at the same time, so larger resource state is more difficult to make in hardware, but at the same time, it also has a higher threshold for both erasure error and Pauli error. And realistic down selection will depend on more information on the hardware implementation of resource state generation and fusions.
Can I ask a question real quick? I might, but what was the 3 times 4 in that column?
So this means like 3 times 4 means like in the unit cell, there are 3 resource states and all of them have 4 qubits. So in the qubit case, there is a 1 resource state in a unit cell, and in the 4-star case, there are 3 resource states in a unit cell.
Okay.
Yeah.
Cool.
Yeah, thanks for the question. So next, we will talk about some equivalent perspectives on the fusion complex, and they will help us to gain more insight into the construction. So first is the dual complex, the dual picture. So on the left is the translation from the fusion complex into its dual structure, the dual complex. So dual here means the usual dual for a cell complex, where the vertex goes to cells and edges goes to faces, cells goes to vertices. And after this translation, the fusion complex condition, which is all edges have 4 incident cells, becomes all, so edges go to faces, all faces have 4 incident vertices, which means all faces are 4-sided. And the dual complex picture provides a very clear operational interpretation of fusion-based quantum computing. So in this fashion, so a surface in the dual complex represent the current surface code state on the unfused qubits in the process, like in the animation we showed before. And then we have a new cell here, which represents an incoming resource state, a new state generated by the resource state generator. And then we perform the fusion at the matching faces. And after the fusion, we get an updated surface. And this represents the new surface code state. So in this picture, in the fusion complex, we are actually making larger and larger surface code state by fusing the smaller ones. Remember, each resource state is also a surface code state. So we are expanding the surface by performing fusions. So this is the dual picture. And also previously we mentioned there. So yes.
So when you expand the surface, this surface code is still encoding 1 logical qubit, right?
It depends on the boundary condition. So here I haven't talked about the boundary condition. So we have 3D complex, we can have different kinds of boundary conditions. So same like Tauri code versus like planar code. So number of qubit code, number of logical qubits will depend on the boundary condition. So there are more information on this in the logical blocks paper, also from PsyQuantum. And so later I have like citation for that.
Thanks.
Yeah, thanks for the question. So previously we have mentioned that there is such kind of triple structure where an edge in the fusion complex representing a fusion and an edge in the XX decoding graph representing an XX fusion outcome and an edge in the ZZ decoding graph, they cross each other into this triple. So this kind of structure leads to 3 related cell complexes. And the first one here is called the R homology complex, or resource state, so R here stands for resource state. So this is the same as the dual complex which I showed before. So in this complex, all the faces are from the XX and the ZZ crossing. And cells in this complex represents resource state, just like in the previous slide. And surfaces in this complex, also from previous slide, represent surface code states. This is the first one. And the one in the middle is called the X homology complex. So in this complex, all the faces are from the fusion and the ZZ crossing. And in this complex, the cells represents XX parity checks. And now we have a homology. So trivial surfaces in the cell complex represent product of XX checks, which is also an XX check. And the non-trivial surfaces in the cell complex represent X logical correlations. So briefly speaking, X logical correlation tracks the evolution of logical X operator in space-time for the quantum computation. And please refer to this paper, the logical blocks paper from PsiQuantum, on more details on the logical correlations. And similarly, we also have the Z homology complex, where all the faces are from the fusion and XX crossing. So just please note that for all three cell complexes, all the faces are four-sided, exactly like the fusion complex condition for the dual picture. And this has an interesting consequence, which is we can arbitrarily permute the three elements of the triple, the R, the X, and the Z, and we still get a valid triple. For example, switching the X homology complex and the Z homology complex, corresponding to switching the Pauli X and the Pauli Z stabilizers, and switching the R complex and X complex, corresponding to switching two stabilizer identities, one within the resource state, because it's a surface code state, so all X stabilizers multiply to identity. And there's also a stabilizer identity for the fusion outcomes, the X parity check. And similarly, we can also switch the R complex and the Z complex. So on the right is the example of the switching of R and X. So it transforms the qubit complex into the alternative qubit complex. Just note here that the resource state size and X check degree here and here indeed got switched. So next, we want to show that our results for the fusion complexes can also be applied into other flavors for fault tolerance. So here is a list of familiar flavors for fault tolerance. So we have a fusion-based quantum computing, or FBQC, circuit-based, or CBQC, and measurement-based, or MBQC. The different flavors have different primitives for physical implementations, and also have different realization of fault tolerance. So in the fusion-based case, the primitives are the resource state generations and fusion measurements, and the fault tolerance is realized by parity checks on the fusion outcomes, just like in the fusion complex picture. And in the circuit-based case, the primitives are repeated measurements on data qubits, and the source of fault tolerance is achieved by the consistency of repeated measurements. And in the measurement-based case, the primitives are the last state, single qubit state preparations, controlled Z gate, and single qubit measurements. And fault tolerance is achieved by the parity checks on the single qubit measurements. So in this unifying flavors paper from PsiQuantum, we have shown that the different flavors for fault-tolerant quantum computing can be unified by the ZX calculus. So basically, different flavors share the similar kind of ZX diagrams, but they have different interpretations, different physical interpretations for the vertices and edges in the ZX diagram. For example, here is a comparison between the circuit-based flavor and the fusion-based flavor. So let's look at edges in the ZX diagram. In the circuit-based flavor on the bottom, so an edge in the ZX diagram can represent a qubit idling, like here, and also part of the C0 gate, like here. So that's edge in the circuit-based case. And in the fusion-based flavor on top, all edges represent type 2 fusions. So that's a different interpretations of the edge in the ZX diagram. And for vertices, similarly, so in the circuit-based case, a vertex here can represent, for example, ancilla preparation, ancilla measurement, and so also part of the C0 gate. But in the fusion-based flavor, all vertices in the ZX diagram represent resource state. So it is possible to reinterpret the same ZX diagram into different flavors for quantum computing. And this kind of reinterpretation allows us to generalize fusion complexes to fault-tolerant complexes. So here is the rough idea. So we can start from a fusion complex, and we draw the underlying ZX diagram, and we identify the Pauli webs on the ZX diagram. So these Pauli webs come from the parity checks on the fusion complex. So after this expansion, we have a ZX diagram with Pauli webs. And then we apply the reinterpretation and translate this ZX diagram into another flavor, a target flavor. And in this process, we might need to apply some rewriting rules on the ZX diagram. And finally, we want to reinterpret the previous parity checks as Pauli webs. So previously, the parity check was the source for fault tolerance in fusion-based quantum computing. But after the reinterpretation, the same Pauli webs, but now with a different physical interpretation, will be the source for fault tolerance in the target flavor. So finally, there are some further generalizations to the fusion complex construction. So we can also define fusion complexes, but not for surface code, for color codes, this time for color codes. So in this case, the resource states are color codes, not surface code, and the logical blocks are also encoded in color codes. That's one generalization. And we can generalize the previously mentioned 3D lattice that represents the fusion network into higher dimensions. And lastly, there is a connection between the fusion complex structure and the 3D subsystem codes. So please refer to the paper for more details on this. And finally, is a recap of the main results. So I hope I've convinced you that there is a really nice synergy between fault-tolerant complexes and the ZX calculus. So we are looking for more communication with the ZX calculus community in order to design better and better fault-tolerant protocols. Thank you very much.
All right, thank you very much for your talk.
Thank you.
People can use the clapping function in Zoom if they want to thank the speaker. Okay, do we have any questions from the audience?
Yeah. Can I please ask about the difference between doing this for surface code versus color code versus other thing?
Yes.
So,
Yeah. So I think, yeah, so is there any specific point you want to address?
Well, so you had in the first part of this talk, you said there's a really simple criterion for coming up with these.
Yeah. That in terms of that, yes. So color
that
code,
will give you a surface code kind of thing.
Yeah.
And is there a similar criterion for the color code?
yes. So for color code, it will be all edges have 3 incident cells, and the cells are 3 colorable.
Okay.
Yeah.
Cool. And then what do you mean by the resource states are color codes in that
So it
case?
means that, it means that if we use the similar kind of like analysis like here, and we write down all the resource stabilizers, that will be like color code. So every qubit participates in 3 parity checks in 3 different colors. Oh, sorry, 3 stabilizers in 3 different colors.
Okay. How does that make it a color code? This is probably this is me being.
Oh yeah. So it's like I think that's it, right? So if you have like a surface and every vertex in the surface have 3 incident faces, and the
Mhm.
faces can be 3 colored. That's by definition, that's a homological color code.
Hmm.
Mhm.
Okay,
Yeah, thanks.
thank you.
Right. Sarah?
Thank you for the talk. I
Mhm.
wonder, is it possible to use this this protocol search like technique to find LDPC codes given like a geometry?
Yeah, I think that is a really good question. So I think I think there is no obvious way of doing this, because LDPC codes will require in general long range connections. And here is like in the 3D cell complex, it seems everything is local. And yes, that's also leads to a really nice point I haven't talked about. So by this ZX diagram, like translation. So I just talk about one direction of this. So from a fusion complex, we can generate protocols for other flavors, but we can also do it in the reverse direction. So for example, there will be a surface code like a protocol in circuit-based computation based on LDPC code. So there exists such things, and we can apply the rewriting rule in the opposite direction, and we will find a fusion network. But in general, that might not be a fusion complex, but we still get a fusion network. We get like a valid FBQC protocol. So on top of like providing more structure of like more examples for fault tolerance for other flavors, we can also learn from other flavors. Yeah.
That's
Yeah,
really
that's another question. Yeah.
And I wonder, is it possible to use this unified framework to have 2 different types of code so that we could use one for memory and the other for execution? For example, if we're using the active volume architecture, then we always see that there's a working memory and there's another memory that used to store the logical blocks. So can we use LDPC code to store the logical blocks, and for the surface code or some other codes like color codes to do the like active execution?
Yeah, I don't know if I could answer that well. So maybe I will need to get some feedback from the colleagues and get back to you on that question. Yeah.
Right, Lucy?
Oh, hi, thanks. I guess since Sarah asked a question about the interpretation, I mean, you can generate something new from like, reinterpret the these are just networks. I mean, they're not necessarily complexes, but or maybe they are, but what properties does the resulting reinterpretation have? Isn't that an important question besides just going through the motion, but is it as much preserved, like what does properties translate to each other or stuff like that?
Yeah, I'm not sure if I understood your question. What kind of property to preserve, you mean?
I don't know, like let's say you go from circuit-based to fusion-based. Let's say your circuit-based has some, maybe you did that already. Like nice property, I mean nice, like maybe, like I don't know, like could be whatever works well makes it a good thing for fault tolerance for the in the fusion-based
I see.
methods. But if when you translate to circuit-based, does it make it a good thing? I mean,
I see. That's a very good question. I think different flavors for quantum computing really depends on like for each hardware implementation, which flavor is most natural, right? So for example, for linear optics, at PsiQuantum, the fusion-based is most natural. And I think it's a very important question to like to think about when we do this translation. Some nice properties for one flavor, does it translate to nice properties to the other flavor? So I'm not addressing this question in this talk, but it's a really good question. Thanks. I think in general, at least one thing is like when we do the Pauli web, we still want the check degree to be small, right, for decoding. So that thing is kind of similar, seems to preserving during this translation.
mm-hmm.
Yeah.
Mm-hmm. And so when you say, for instance, cells that comes to like, oh, so first of all, you're not talking about boundary condition. You're assuming for now that the complex extends forever, so that whatever the picture doesn't, you don't interpret the boundary of that.
Right, right.
And then so, but you come up with that mostly because you started with the the current protocol for fusion-based quantum computing, and you are analyzing that and say the resulting things are this, but you're not saying that only complexes with this property will give good fusion-based quantum computing protocols, right? You're not saying that, you're just claiming one way. It's just not a necessary condition, but I mean it follows one way but not go the other way. Because I was looking at when you say you ought to characterize what's the important criteria for it to be successful fault-tolerant protocol, on the fusion base or whatever method interpretation you're doing. Then I might think, well, when you say criteria, maybe it's a necessary and sufficient condition. I guess not. Like, right? Like that's not what you're doing. You're just analyzing example, still by example. And
Yes.
Okay.
That's right. Yeah. Thanks for the comment.
Thanks. Sorry. Just clarifying. Thanks.
Okay, any other questions from the audience?
I have a question about the.
Giovanni, Leah raised their hand. Just
Leah, okay, nice.
Leah
Oh,
first.
it's okay. Giovanni, you can go first.
No, Leah, you go first.
No, you already went first.
Okay, well, I guess my question is about fusion measurements, and in terms of fusion-based quantum computing, or you mentioned FBQC protocols that implement these fusion operations. So I have two questions. Is like, what are for you like possible fusion operations? Do you use always the same type of fusion? And what is an execution like in the machine? What is the protocol?
So this talk focus on the type 2 fusion, which is like 2-qubit measurement. But FBQC is more general than that. So FBQC is like a model that we have small resource states and we have field body measurements. So we have more general field body measurements, like 3-qubit measurements and even more. So those are possible. And the implementation in the hardware is at PsiQuantum, we do it with linear optics. So using the linear optical elements.
Yeah, so you mainly use type 2, and I suppose also bigger ones too.
Yeah, we can use other bigger ones. Yes.
Okay, nice. And in terms of protocols, what is an execution of this measurement? What is a protocol? An FBQC protocol?
Oh, you mean how is the measurement implemented in hardware?
Yeah.
Right. So basically, like we are using linear optics. So we have photons and we route them, and then we use linear optical elements, and then we do photon detection. So things like that. Yeah.
Yeah. So okay, it's starting from the So this is all in the model where you start with these hexagons, right?
Yeah.
Okay.
Yeah. Thank you.
So Leah, it's your turn.
Could you go back to the slide with the table of your probability of erasure versus Pauli flip errors?
Yeah.
Thanks. Well, my question is about I didn't understand how the error model was decided. So how did you come up with quantifying the fusion success probability along with the probabilities of how much erasure and Pauli flip you could have? Like, do you have to compile it knowing how much delay each photon has? Or,
or
how did you estimate that?
Yeah, I think for the purpose of this talk and this paper, it's more academic. So we're actually using a very simplified error model, which is not realistic for hardwares. So here in this model, we are assuming that all the fusions in the lattice, they have the same erasure. So all the fusion outcomes in the lattice, they have the same erasure probability or the same Pauli flip probability. So this is not realistic. So as I mentioned before, like this table is only for this ideal, like a simplified error model. And when we want to perform the real down selection for specific hardwares, it will depend on more information on the hardwares. And there will be a more realistic error model for that.
Thank you very much. Would you have a reference for learning about error models for photonic hardware? Or for
Yeah,
linear
if I,
optical qubit hardware?
yes, if I find some, I can send it to you. Yeah.
Thank you.
Okay, Lucy?
Thanks. Yeah, sorry, I have a couple more questions. One is that, so I guess you have this ZX network or something, right? And then you have the polyweb on top of it. And polyweb tells you sort of at least which ones it acts in terms of the stabilizer, at least. But do you
Yeah.
also is the that's just for the stabilizers, the webs, it's just overview.
Yeah.
And what's the rest of the rest of it gives you information what about parity checks, or I mean, what is it the rest of it? The rest of it doesn't change in your selected your way of doing the computation.
Yeah.
When does it change? When does it not change? I mean, like a little bit of what information does each of this encode, like in the
What do
overview.
you mean by changing here?
I mean, so you could potentially, I mean, I guess neither of them change, maybe because your 156 are polywebs, given the thing you both are fixed, maybe the highlighted one and the non-highlighted one are both. The polyweb and the underlying network are all the same. But okay, I mean, maybe it's just additional structure. And I was pretty intrigued by your 3 complex interactions. You know, I mean, it'll be nice to see. I mean, I don't know if you did like show pictures of how the different complex subcomplexes look like. I suppose that's what they are, right?
Subcomplexes. You mean
Or
like,
maybe just how 3 different complexes all taken out.
you mean this one? You mean this one?
Yeah. So like they're kind of, I mean, are you picking out 3 different subcomplexes within the same?
Oh no, it's like we have a fusion complex and then we can apply different transformations to get different complexes, not subcomplex, but an entirely new complex.
Okay.
Yeah.
But yeah, what is the transformation exactly?
The transformation is like in the fusion complex, all the edges, I mean in the dual fusion complex, all the faces are here.
I see.
And then instead of using these things as faces, we can use these things as faces. And that gives us a new complex.
The different geometry gives you
Different geometry, yeah.
Even though the 1Ds, so
One
the one
skeleton is also
skeleton
different.
thing-
One skeleton is also different.
also different?
Also different, yeah. So here the
But
one skeleton will be like the vertices will be here and the edges will be around here, right? In this case, the edges will be around here.
Let's say the 1 cells are the same, right? I guess.
The 1 cells are the, I don't even think so. So for example, like in the 1 cells here are the endpoints of the X and the ZZ edges, but the 1 cells here are the endpoints of the fusion and the ZZ edges. And the endpoints of the XX like edges will actually be on the centers of the cells in this complex.
Okay. May take a little bit absorbing. I think it's kind of cool to have.
Yeah, I agree. This part is a little bit difficult to understand. And there
and which is the complex that you originally constructed was using which one is this? That one? The one?
The original one is this. The original one is not even this one. So we first from the original one, then we construct the dual complex, so as here, and the dual complex like is this one. And starting from here, we can generate the others. Yeah.
And that's how you get new kind of particles. One way to get new particles by rotating this.
Yes, right.
It's the triple that mattered. You need all 3 to.
So it's like one message we want to show here is that usually in fault-tolerance we often talk about primal and dual, right? But for fusion complex, it's not simply primal dual. It's 3 things. It's a triple. Yeah.
But none of them is the original one.
Right. Yeah.
But all of them can come from the original one.
Yes. So for the original one, there is also a triple for the original one, which are the duals of these two
Duals.
things. Yes. Yeah. Yeah.
So you need the 3 because you need to capture the fault-tolerant properties of this thing. They all tell you something different about the fault-tolerant.
Yeah, in this case, it's the 3 things correspond to fusions and XX decoding and ZZ decoding.
Thank you.
Yeah, thanks.
Okay. See, Sarah, there's your hands raised.
Thank you. So may I follow up on Leah's question about this noise model? I'm curious, like whether when you're finding different protocols, have you tested how like the results is affected by your assumption of error models or like the noise profile of your architecture? Like how much will that change?
Yeah, that's an important question, like internal at site. But I'm not sure how much I can share on that. Thank you. That's an important question. Yeah. So just the thing I mentioned here is that realistic down selections will really depend on hardware models, right? And for different kind of, so for example, you can also maybe implement FBQC not using linear optics, right? And in that particular implementation, you might have a different like kind of down selection from these complexes.
If I may ask one more question,
Yeah, sure.
how big of a search can you do? Like
Yeah,
say
good
roughly
question. Yeah.
or what kind of codes or system size
Yes.
can you search for with the iterative algorithm?
So here, that's a really good question. So in the paper, we talked briefly about this. So here on these Delaney symbols, you see the first integer here, 1, 2, 5, 2, 4, 8, this integer, it so-called size of the Delaney symbol. So basically it's like
I don't think you're sharing your screen. Are you trying to share your screen?
Oh, I'm not showing my screen. Okay, let me
I
do
think
it.
he is. Huh?
Oh, okay. Maybe let me see if it's on. Oh, I see it now.
I see now. Yeah. So here, like the integer here is the size of the Delaney symbol. And the organization of this like software here, Gavrog, is such that you search for the cell complexes, but the search is bounded by the size of the Delaney symbol. So generally speaking, the larger this number is, the more complicated the cell complex is. So our search is like, we are in the paper, we showed the results like searching over Delaney symbols up to size 15. And we got a bit over 600 examples. And we ran that on our on a laptop, and it took about like several days, the search. So this search is not like, it seems the complexity, so I'm not exactly sure about this, but it seems the complexity of this search, when you increase the size of the Delaney symbol, it grows very fast. Does that answer your question?
Yeah, it does. Thank you.
Sorry, what is